Oh, you're here. That must mean it's time for another math lesson. Let's get started. Here we are in lesson 5.1. Whoop. So solving polynomial equations. Again, this is 5.1. Let's make our screens a little bit bigger. So I can use the rational roots theorem. Seems like we're going to learn a theorem to determine the roots of a polynomial and to find solutions to the polynomial equations. So we are going to try to solve them using this rational roots theorem. So let's see what they got for us. So the county commissioners are discussing the total attendance at past county fairs. They remember that in one recent year, but can't remember which, the total attendance was exactly 100,000. A county statistician created a model for the attendance of the fair over the time period 2005 to 2020, which includes the year of the total attendance of 100,000. What mathematical questions can you ask? So obviously if we can get that equation that he came up with, then we could solve and figure out what year they reached 100,000 people. And then from that year, they can figure out what they did right, so hopefully they can continue to make their fair better. So when you first looked at the image, blah, 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 and look, there is the function that they have. Now, originally, when we just had a squared function, we could kind of solve for that. So now it's a little bit tougher, but that's what this is all about. We're going to try to figure out how we can solve this. So let's get started. By the way, down here it says, how can I use the model to determine the year of the total attendance? So that's just very simply, if you take this function and you set it equal to 1,000 and then solved, that's how you would do it. But that process is a little bit harder than it sounds, but that's ultimately what we're going to do, is we're just going to solve these functions. So let's go. So we're going to try to solve polynomial equations. But first we got to learn a couple of words. So relate zeros and coefficients of polynomial functions. So a root of a solution. So a root is a solution of the polynomial equation f of x equals 0. A zero of the function, f of x is any value of x for which f of x equals 0. Thus, the term root is used when referring to an equation, and the term 0 is used when referring to a function. The zeros and the coefficients of any polynomial function p of x are related in a specific way. Any constant c can be rewritten as c times x of 0. For example, the constant 4 can be rewritten as 4 times x to the 0. So any number times the 0th power is equal to 1. So the constant of a polynomial function is also a coefficient of the function. So what that means is we've got the zeros and we've got the roots. So roots generally are talking about things like this. So roots are generally functions, whereas a zero is a number. So like f of x equals 0, x equals a number, that's going to be a 0. So they are closely related, but they are slightly different. So again, these are examples of roots. Zeros would be like x equals -4, -1, 1, and 4. So, that being said, as we scroll down, I think that's what they're going to ask us. So, the function f of x equals all of that stuff is a polynomial function written in factored form. So, they conveniently already factored it. If you were to graph it, note that our zeros, otherwise known as when it crosses the x-axis, correspond to our zeros. So I guess I got to erase my dots. So what are the zeros of f? Select all that apply. So we've got -4, -1, 1, and 4. And then how does the function f appear when written in standard form? So that is just going to be, when we multiply this all out, which, if I were to just take these right here, so that's going to end up being a difference of squares. So that's going to be x squared minus 1. And then we have x plus 4, x minus 4. Again, another difference of squares. So I'm using all of those patterns just in reverse right now. So we've got x squared minus 1, and then x squared minus 16. 4 times 4 is 16? Yeah, we'll go for that. So then that kind of makes it a little bit easier to multiply everything out. So now I'm just going to FOIL it all. So we get x to the 4th minus 16x squared minus x squared plus 16. So we're going to combine like terms. X to the 4th minus 17x squared plus 16. So is that one of our options? There we go. Oh, so what are the coefficients of f? So as we go through, we've got a coefficient, and a coefficient. So those are the numbers that we're looking for. Whenever you don't have a number, it is assumed to be 1. So we've got 1, -17, and 16. So how are the zeros of the function related to the standard form of the function? So the zeros can be found by factoring. So, let's come back here. So the zeros are multiples, right? What are our zeros? Of the constant term 16, right? So our zeros, we'll just come back up here. Our zeros were 4, 1, -4, -1. Those are all multiples of 16. Interesting. Let's see where that takes us. All right, so here we go again. Now we just have a different polynomial. So consider the polynomial function that there's our graph. Note, we have our zeros everywhere where it crosses the x-axis. I'm just going to go ahead and write my zeros up here. So again, these are our roots, and our zeros would be x equals -3/4, 1/2 negative, and then +1/2. Okay, so let's scroll down. I'm sure that they're going to ask us this stuff now. So what are the zeros of g? Select all that apply. They put them in decimal points. Sometimes I get irritated at decimal points, but whatever. Great thinking. So how does function g appear when written in standard form? So I need that original function again. And let's play this game. So here we go. I'm going to FOIL out. Actually, no, I'm not. I'm going to start here because that looks like it's going to be difference of squares. So 2 times 2, or 2 squared, is going to be 4x squared minus 1 squared times 4x plus 3. So now we'll just FOIL it out. Did I do that right? Yeah. No. Back up. That should not be there. That makes a whole lot of sense. I knew that looked wrong. So, okay, so we've got our difference of squares there. Now we're going to multiply it out. So 4x squared times 4x is going to be 16x cubed plus 4x squared times 3 is 12x squared minus 4x minus 3. And we have no like terms, so there we go. It is in standard form. Is that the right one? Cool. Using the distributed property. Yay. So what are the coefficients? So again, the coefficients are the same as if we were going to set it up for synthetic division, but those are our coefficients right there. So 16, 12, negative 4, negative 3, something like that. Now here's the interesting part. So how do the zeros of function g relate to the standard form of the function? So again, here's our zeros. Here's our coefficients. We should specifically look at these two coefficients. So I guess it doesn't matter which one we start with. So we'll say the numerators of the zeros are factors of the constant term. Is that right? So this is our constant term right here. And then the denominators are, actually I guess I should be using the word multiples of the leading coefficient. No, okay. They were factors, I'm sorry. There you go. So this is actually what this is kind of all about. You kind of proved how this next part's going to work. So, man, there might be a theorem about this. I told you there's a theorem. So find zeros using the rational zero theorem. So the rational zero theorem can be used to determine the rational zeros of a polynomial function. The theorem is based on the observations you made in task 1 and 2. The zeros of a polynomial function are related to the coefficient when the function is written in standard form. So here is the rational zero theorem. So if p of x is a polynomial function with integer coefficients, and if m over n is a zero of p of x, that is p of m over n equals 0, then m is a factor of the constant term of p of x, and n is a factor of the leading coefficient. So to break that down, so when it says m is a 0, then m is a factor of the constant term. So here is our constant term. N, as in November, is a factor of the leading coefficient. Here's our leading coefficient. So let's try an example. So it says use the rational zero theorem to determine the rational zeros of the polynomial function. So as we mentioned, the leading coefficient right here is 1, because remember, if there's no number there, it's assumed to be 1. And then our constant is this guy. So that means, again, if we go back up here, m over n, and I'm always going to get these wrong. So m is a factor, so n is the leading coefficient, and this is the constant term. So since our leading coefficient is 1, that's going to help us out a lot. It's going to make this a little bit easier because all of our numbers are just going to be divided by 1. So, okay, too easy. That means that all possible rational zeros must be factors of 42. So we can really focus on this number at this point. So if we list out our factors of 42, so we've got 1 times 42, 2 times 21, 3 times 14, and then 6 times 7. So, and then all of these are plus or minuses on all of them. So those are written right here. So now what we essentially have to do is we have to divide each one of these factors by our polynomial up here and then figure out which ones works. So really what we're doing is we're going to take each one of our factors and let's say, start with 1. So it's going to be like x minus 1, x cubed minus 8x squared plus x plus 42. So we're going to do that for every single one. So for x minus 1, x plus 1, x minus 2, x plus 2. Now that could start taking a long time. So that's why we did so much practice with the synthetic division. We can go through that pretty quick. So if we start with just 1, 2, and 3, let me find some white space here. Oh, close enough. So start with 1. I need our function again. So our coefficients are going to be 1, negative 8, 1, and then 42. So 1, negative 1, negative 9, 9, 10, minus 10, 32. Okay, so we have a remainder there, so that's not 1. That's not a 0, or I guess that's not a root of this function. Okay, so now we're going to try 2. And remember, when we say 2, you always take the opposite of it, because that's what how you would set that root equal to 0. So here we go. So again, it's 1, negative 8, 1, 42. 1, negative 2, negative 10, negative 20. Oh shoot, that'd be positive. That'd be 21. 21 times negative 2 would mean negative 42. Bam, 0. So we have 0 as a remainder. So our negative 2 is a function. So you'll notice if you look at my chicken scratch versus the ones that they picked, so they just used the positive numbers. I was using the negative numbers. I got a little confused, but hey, I still found one of our roots. So we can go through the same process using the one that I found as opposed to the one that they found. And you'll see at the end that it's all good. So again, they just used our positive ones right here. I just used the negative ones. That's all. So here we go. So the table or my little chicken scratch right here shows that our negative 2 is a 0 or is a root. So I can rewrite our equation as x plus 2, because note, when I put that negative 2 in here, it turns to 0, times, let's see here, these ones that we have right here. So that would be x squared minus 10x plus 21. And then from there, you could do the same process all over again. But at this point, you could probably factor it. So like, if you take 7 and 3, that would give you 10. So you can just factor this guy right here. X minus 7, x minus 3. So our actual zeros, we'll bring our x plus 2 down. Our actual zeros are x equals negative 2, 7, and 3. So again, this is just a different, they just found a different root, but we found that same root eventually. So this shows you it doesn't really matter which direction you go. It is kind of guess and check. I would find a logical way of guessing so that you're not just picking random points. So can you use the rational zero theorem to factor the trinomial? I would say yes. So no, the rational theorem does not apply. That's false. You need to use synthetic division in order to factor the trinomial. Kind of. Yes, the rational theorem applies. You do not need synthetic division. Yes, the rational theorem applies, but you need synthetic division to factor the trinomial. I mean, I would say yes, but you do not need synthetic division. Hey, look at that. And so here's their answer that they got, which you will notice is the same that we got. Right there. So we have successfully found the roots and the zeros of the function. Here are our zeros. Here are our roots. So again, our roots, our zeros. Make sense? Great. All right, so let's try another one. So it says find the zeros using the rational zero theorem. So use the rational zero theorem to determine the zeros of our polynomial function, right there. Since the leading coefficient is 1, so remember when it's not there, it is assumed to be a 1. All possible rational zeros will be factors of negative 100. So having a 1 right here makes it a little bit easier for us. Having 100 right here makes it a little more challenging. There's probably a lot of factors there. But hey, we'll figure it out. So does the fact that the constant term is negative affect the possible rational zeros? No. The values of each factor will still be positive and negative. Yay. So they just so conveniently list out all of our factors. So again, the way they found that, they had negative 100. They went, you could do 1 times 100, 2 times 50, 3, no, 4 times 25, 5 times 20, and then 10 times 10. So here are all of our factors, also listed right there. So that's where they got them from. So they set up this nice little chart right here that I think I'm going to totally steal. So it makes it a little bit easier to do the multiple synthetic divisions. So this chart, or this column right here, is your possible zeros, the numbers. That would be like the number that goes right there. And these are all your coefficients. And here's going to be your remainder. So again, I'm going to steal that chart. So we'll put it in red. So our possible zeros, or our coefficients, going across are 1, 5, negative 21, negative 125, negative 100. Let's give ourselves a little bit more white space here. So we're going to make a line right there. So this is really kind of slick what they did. Like I'll give it to them. I kind of like it. So we've got our synthetic division set up. So we're going to start with 1. So the first number comes down. 1 times 1 is 1. No, that's not what they were doing. So 1 times 1 is 1. You're going to add it to 5, so we're going to get 6. 6 times 1 is 6. You're going to add it to negative 21. So negative 21 minus 6. Or however you want to do it. So negative 15. Yes, I'm cheating because I grabbed a calculator. Whatever. Negative 15 times 1 is negative 15. So add that to negative 125. That's negative 140. Negative 140 times 1, negative 140. Add that to negative 100. It is negative 240. So now I already have my chart. I just go to my next number. So we're going to just continue with our positives. So first number comes down. 1 times 2 is 2, plus 5 is 7. 7 times 2 is 14, positive 14. So negative 7. I should be able to do this in my head, but whatever. So negative 7 times 2 is negative 14. Right? Yeah, negative 14. then you add that to negative 125, negative 139, negative 139 times 2. This is where having a calculator is handy. Negative 278, add that to negative 100, negative 378. Let's check my answers. Yep. So we keep going. We hope at some point we hit one, and then our lives get easier. But until we do, we're going to keep chugging along. So first number comes down. 1 times 3 is 3, plus 5, 8. 8 times 3, never good at my 8s, 24. So that's a positive 3 when we add it to negative 21. 3 times 3 is 9. Add it to that guy up there, the negative 125. Negative 116. Negative 116 times 3 is negative 348. Minus another 100 is negative 448. Just make sure I didn't screw anything up. Uh-oh, looks like I did. Where did I mess up? Man, I just did 3 and I didn't need to. Mr. Lin. Jeez. Can't take you anywhere. So you can see 4 down there. We're going to speed this process up. And look, 5. That seems like a good number to go. 5. So bring 1 down. 1 times 5 is 5. Add it to 5, you get 10. So then you times 5 is 50. Oh, 50 minus 21. 29. 29 times 5. 145 minus 125 is 20. 20 times 5 is positive 100. Oops. Positive 100 minus 100 is 0. Thank goodness. So here is our 0. From our 0, we can figure out, or we can determine our root. So our root is just going to be x minus 5, because when we plug that 5 in, that should hit 0. So then our remaining numbers are these guys right here. So there's 20, 29x, and 10x squared. Clearly I did that wrong. Where do we start with? Where's our first equation? Oh, yeah. So I assumed that we were still dealing with a polynomial to the 3rd power. That was my mistake. We have a polynomial to the 4th power here. So after we take 1x out, starting from this side right here, we're going to have x cubed plus 10x squared plus 29x plus 20. I ran out of space there, but luckily the books got our back, because they got this right there. So now we get to do this all over again. I know you're excited about this. So we can apply the rational zero theorem again, since the leading coefficient is 1, all possible rational zeros will be factors of 20. So now we can list the factors of 20 over here. So we got 1 times 20, 2 times 10, 3, 4 times 5, and then 5 times 4. So we got a lot less this time. And you will notice that we've already done a couple over here. 3, because I'm a crazy person. And obviously 5 doesn't count either, because we already did that one. So we just knocked a whole bunch of them out. So all we have to worry about is -1, 2, -4, -5, plus or minus 10 or 20. So let's clear up some white space. So we talked about why some of the factors are missing, so we've already done it. So, hey, look. So if we started with -1, that's going to get us a remainder of 0. So again, they just use synthetic division right here. So then we have this left. So from there, so we know that we already have x minus 5. Now we know this is a 0, x plus 1. Remember, because when this gets plugged in, this needs to equal 0. And what do we have left over? So that would be x squared plus 9x plus 20. So 20 added together. So I'm I'm doing my traditional factoring here. Added together, 4 times 5. Bingo! So we can just do x plus 4, x plus 5, x plus 1 from right there, and then x minus 5 right there. Voila. So the more you do it, the easier it gets, but sometimes you might have to use this theorem a couple times over in the same problem to get to the end. Man, we did all this work, but you know what I'm missing? I'm missing a good old-fashioned word problem. Let's do one. So here we go. Solve an equation using a rational root theorem. So this is just the root theorem over again. A resort rents beach cabanas that are shaped like rectangular prisms. Each cabana has a length, I'm going to write this down as we go, 4 feet less than twice the width, so 2w minus 4, and a height of 1 foot less than its width. The least expensive cabana for rent is shown in the photo. What are the dimensions of this cabana? Notice that it tells us something right here. The space enclosed by the cabana has a volume of 420 cubic feet. So we know that our volume, I'll write that over here, equals 420. And since we're going to find our volume is going to be length times width times height. So our width is equal to our width. Turn that to x if you want. I don't care. Doesn't matter. So we need to find the dimensions. We have a given volume, so first we need to find the volume ourselves using the dimensions. So again, length times width times height. So we've got 2w minus 4, w minus 1, and then w. And that equals 420, because that is the volume of our cabana. It's quite adorable. So what we're going to do, we've done problems like this before. We're going to multiply everything out, minus this over, set it equal to 0, and start solving, right? So let's see here. Y are the expressions in terms of width, because that's how the problem gave them to us. There we have our equation that we already made. What formula was used to create this equation? Length times width times height, which is a volume equation. Nice job. So here we go. We're going to take, this times this, then times that, and then, hey, look, this is what we got. So remember, we got to there by foiling all this out, and then we subtracted 420 from both sides, and we combined like terms. Right? Cool. So we'll just take that. Save you guys some time. Why was the equation rewritten? Honestly, so that it can incorporate the volume and then give us something that we can solve. So now we have this thing, and it is equal to 0. So now we can just solve it, right? Just like we've been doing. So since our leading coefficient is 1, our constant term is negative 210. So the only thing we're going to be worried about is the negative 210. So we're going to list out those factors. So I totally know those off the top of my head. So obviously 1 times 210, 2 times 105, 3 times 70, 4, ooh, I don't know what 4 is. And I'm just using my calculator for this stuff. Don't beat yourselves up with something like that. 4 is not easily divisible. 5, 42, 6, 35, and so on and so forth. So again, they list them all out. Trying to save you guys as much time as possible, not watching me just do simple math or arithmetic. So now we need to start testing all of these possible roots. Hopefully we find one towards the beginning, and we don't have to do a whole bunch of crazy ones. So again, I'll get you started. So if we do our chart, our coefficients are going to be 1, -3, 2, negative 210. And our list of coefficients, I'm just going to start with positive 1, start making my way through. So if I do 1, bring the 1 down. 1 times 1 is 1, plus negative 3 is negative 2. Negative 2 times 1 is negative 2. Plus 2 is 0. 0 times 1 is 0. Minus 210. So that's not it. 2. Bring the 1 down. So 2 plus negative 3 is negative 1. Negative 1 times 2 is negative 2. Plus 2 is 0. 0 times 0, 0 times 2 is still 0. So negative 210. Did I do all that right? I have a bad feeling about that. Oh, that's fine. So 3 was one of our factors, right? So bring the 1 down. 1 times 3 is 3. So minus 3 is 0. 0 times 3 is 0. So we got 2. 2 times 3 is 6. So we're going to have, what, negative 204. And keep going. And my spidey sense is telling me that 7, I looked ahead, is going to work. So we bring the 1 down. 1 times 7 is 7. So that's going to be a positive 4. 4 times 7 is 28. Oh, plus 2 is 30. 30 times 7 is, I don't know, 210. Look at that. Minus 210 minus 210 is 0. So here we know that x minus 7, because remember that 7 has to go in there, times, so here we had a w cubed. So now we're going to have, I just switched to x's, but that's fine. X squared plus 4x plus 30. Now, is that factorable? That is a good question. 30. I don't think that it is, because it's plus here, so you're going to have to add both numbers together. I don't think we're going to find anything there, at least not the easy way. Which also means we might have to do it the hard way. So we tested possible roots. Since r is a root of the equation, w equals 7, the width of the cabana is 7 feet, therefore the length is 10 feet. So if the first root that you find makes sense in the problem, then you are good to go. So if our w equals 7, then you just take that and you plug it into all of the stuff up top. So you can find width and whichever one was the length and the height. Make sense? Totally. Too easy. Now I got a problem for you. Okay, so what does this look like in the real world? In the real world, if you're going to be finding zeros to something or you need to solve these types of equations, you're going to use a computer, and you might be programming, a computer program or something like that. So that's kind of what I'm about to show you is how that works. So this logic is important to know, but I'm not going to test you on it. So here we go. Find irrational zeros using successive approximations. So the rational zero theorem only works if at least one of the zeros is rational. When the zero or zeros are irrational, things like 2.3333333333 or pi, you can use successive approximations to estimate the value of the zero. Successive approximations are closer and closer estimates for a zero of a polynomial function found by systematically decreasing the interval that contains the zero until a desired place value is achieved. Basically, you start off with like, I know that there's a zero in between here, so we're going to cut it down here, we're going to cut it down here, cut it down here, cut it down here, and you can get infinitely closer, but it's an irrational number, so you're never going to get all the way. Practically speaking, you go as far as you need to for whatever your measurements are or you need, and then you're done. So here we have a function that they gave us, and so they show it using Excel, and that's totally fine. And I'm actually going to show you using Excel as well. So we've got that function there. Now, quick tutorial about Excel. Well, actually, let's go back. Let's write down our function. So V of R equal to 10 divided by 9 pi r cubed minus 2 pi r, I did not leave myself enough space, plus 5. So we're going to go into Excel, and in Excel, if you look up here, you can add formulas. So on this side, I just threw in numbers, but these ones, I put in a formula. So notice how the formula starts with an equal sign, and then you enter your formula in, and in this case, when I got to our variable, I just added, or I told it to take your variable from the box right next to you. So that's what all of that means. So anytime you see an A2, that's kind of like the R in our formula. Also, if you notice, there's that little caret sign like that. So that's how you would put things into exponents. So again, everything here is basically going to pull this value, shove it into the equation, and then poop out an answer. So if we go back to our problem real quick, let's see here. So find 3 decimal places when the volume equals 1900 centimeters. So I'm going to write that down too. 1900 centimeters cubed. So if you look at my equation, I subtracted 1900 from it. So theoretically, when all of this number equals 0, then that's our answer, right? Well, I can tell you right now that we're not going to find an easy 0. So if you go down the list here, I just started with 6. I got this big number, so then I kept on going, 7, 8, 9, and notice what happened here. So I went from a negative number right there to a positive number. So that means that my 0 is somewhere in between 8 and 9. So I can write down 8. but we want to go even further. So notice how I put my point here. So now we're going to work on this part. So my next number is 8.1, 8.2, 8.3. Oh, look, I started out negative and now it's positive. Again, my 0 is in between these two numbers. So we'll do 8.2. Okay. So then we go down the list. 8.21, 8.22, 8.23, 8.24. Oh. Gee, what happened? We went from negative to positive. So again, my 0 is somewhere in between there. So we're going to put 8.23. So let's see, 8.31, 8.32, and again, we went from a negative to a positive. My 0 is somewhere in between there. So that was 8.31, and we could continue this process as many times as you wanted. With current computer programming, you could probably go thousands, if not millions, of decimal points if you really wanted to. But in the real world, if this is something that you would be doing, you would very easily set up a computer program to do this process for you. That would actually be a pretty easy program to set up with, or to set up. So then you can then start pumping out these numbers for whatever purpose you need. So that's how that works. If we go back through here, they wanted to go to one more decimal point, which is fine, but so that's basically how that works. Again, this is not something that I'm going to specifically test you on. I already talked to the pre-calculus teacher. It's not something that she's going to use, but it's a kind of a really important concept because this is something that might actually happen in the real world. You might be using either Excel or a computer program to figure these things out for you. You can also like graph it, trace. That's what I did the first time when I was working on this. Whatever kind of makes you happy, right? And how is the spreadsheet used to calculate the radius to 3 decimal places? Yeah, so we went through all of that. So that's how that works. I'll probably go through some of them in class. I'm going to go through the I'll do this problem on the check on learning. I know that there's one in there, but again, don't stress too much about something like this because this is, like working Excel is almost an entirely different class, but might as well expose you to it while we can. So try check on learning. I'll tell you right now, the 5th problem is going to be something like this. Try your best on it. But either way, there's going to be a video, and I'll see you in class.